All right, so Alfredo, if you could share your slides, please.
See it.
In the meantime, I'd like to introduce our first speaker, who is Alfredo Torrico. Alfredo is a postdoctoral researcher under Andrea Lodi in Montreal, and he is working on a variety of really interesting problems that I think that he will be is presenting some of them today. And I've even discussed some recent cutting edge work on how to handle information being spread through various channels that I don't think he'll talk about today, but I think he would be very happy to discuss with whoever wants to afterwards. So with all that, Alfredo, please take it away.
Yeah, can you hear me well? Is everything fine? Okay, good. Thank you for organizing this great opportunity. It's a great chance to spread the word. So today I'm going to talk a little bit of part of my work at the end of the PhD, partially the beginning of the postdoc, around the submodular optimization. So let's get into the problem. So subset selection, I mean, the name sounds a little bit obvious, but this area corresponds to actually obtaining a subset that represents the most of a grand set of elements, of a universe of elements. So for example, in data summarization, we want to obtain a subset of sentences that summarize the most the document or coverage the most the document. And also influence in social networks has been a known application in which people are part of a network and correspond to each node, and then you want to select a subset of the nodes such that maximizes the influence over the network. Okay, so the problem in general is to optimally select this subset according to some valuation. Okay, so which kind of valuation is the submodular type of functions? So let's imagine that we have Heisenberg coming to a food chain, and then he has already a burger on the combo, and then he's offered a drink. Okay, so he really likes this option, but if when he's offered a refill, then it doesn't seem appealing so much as before. So he realizes that this is actually the diminishing returns project. Okay, adding an element to a larger set has less marginal value compared to a smaller set. Okay, so submodular optimization has been around many years, has many applications in different multiple fields, classical applications in operations research, game theory and economics. And recently there has been a lot of interest from the machine learning community and computer science. Many applications, the classical one, sensor location, or data summarization, as already mentioned, influence also. But I want to mention that whenever you encounter the concepts of utility, coverage, influence, or clustering, representation, you may think and you may have some model optimization part of your toolkit. Okay, there is some recent work on diversity and fairness, and especially migration, for example, in which, for example, you want to allocate migrants to new jobs. That's okay. So I hope that you get the feeling of some model optimization. Let's get into the math. So let's assume that you have a ground set of elements. We have n elements, imagine n sensors, and we have a set function. So we have a function that evaluates subsets of B. Okay. That is non-negative and is normalized. Okay, so through the talk, I'm gonna denote the marginal of a set as this expression, and I'm gonna assume two main properties. One is monotonicity, in which is kind of obvious, is the value of a larger set is larger compared to a smaller set. Okay, so and then we have some modularity that, as I already mentioned. So adding an element A to a larger set has less marginal value compared to capital A. Okay, so the problem of interest in submodular optimization is, in this case, maximizing as a modal function monotone according to some feasibility constraint. Okay, well, there are many types of feasibilities. The classical one is cardinality. You also have partition, or more general called matroids, and also you have a knapsack, etc. But even in the simplest one, this is cardinality, the problem is NP hard. And what do I mean by this is that obtaining the optimal solution, there is no efficient algorithm, so you can obtain the optimal solution. That's my point. So what is the natural approach in this case is one natural approach is approximation algorithms. And the protagonist of this talk is the greedy algorithm. It's the one that in each iteration, you add the element with the largest marginal value, okay, while keeping feasibility. The performance metric for this type of algorithm is as I mentioned, is approximation guarantee. So you want to say that the output of this algorithm is at least alpha times the optimal value. Okay, so it's well known by this classical work from Nemhauser, Wolsey, and Fisher that for cardinality constraints you have the 1 minus 1 over E approximation, this 0.632, and for general constraints for called matrix you have a half. Okay, so the greedy algorithm has been used in a lot of other senses. We have also has been applied to partition or matrix knapsack constraints. There have been improvements in speed. For example, lazy evaluation is in which you want to, you don't need to compute the marginal values in each iteration. Or a stochastic greedy, for example, there have been work on that, in which you don't need to evaluate in all the ground set. You just need to sample a smaller set. Some continuous version as well to improve the guarantees. And also 2 new models that have been really, the community of machine learning has been interested in this streaming model and parallelization. So yeah, so greedy algorithm plays an important role in some more optimization. So the first question that I want to address today is the performance of the greedy algorithm. In performance, I mean the guarantee that we have. So we know that it has these guarantees that I already mentioned, the 1 minus 1 over E and the half, but actually in practice it's performing much better. It's actually, sometimes it's giving near optimal values, okay? So for this part of the talk, I'm gonna assume that we have one single submodular and monotone function and just cardinality constraints, okay? So keep it simple. So we know that the greedy algorithm achieves this 1 minus 1 over E, and we also know that it's tight, meaning that without any complexity assumption, it's impossible to improve this guarantee, okay? So what is what is going on? So the thing, why is behaving well in practice? So there might be some property of the function of the data set that we actually not considering. So this has been a challenge over the time, over probably 30 years, in order to describe or find properties of the function in order to obtain better guarantees. Okay, so with this example, with this experiment, in which we want to select the K most informative patients with Parkinson. So we have here a monotone submodular function. You don't need to know more about this type of function, but it's monotone and submodular. That's my point. And I'm plotting here on the x-axis, I have the budget size K, and each of these instances are random. Okay, so and the instance corresponds to size 2K. So for example, we have an instance with size 10, and we want to select 5 elements, and so on. Okay, so we can see in orange that the grid is actually finding near optimal values. Okay, so on the bottom we have 1 minus 1 over E, and on the top we have an approximation factor of 1. Okay, so it's actually finding an optimal solution. On the green, I have the curvature. Okay, this is a concept that was introduced by Conforti and Cornell-Jones in the '84, and somehow tried to explain how smooth is the function, how close to be linear is the function. So so it gives, mathematically, it gives a lower bound on the marginal value. The marginal value is lower bounded by a fraction of the value of the singleton. Okay, so for example, when gamma is 0, we have linear function. And they prove that the greedy algorithm gives this approximation, this improved approximation factor. Okay. So as you can see, there is still a gap that we can fill. And for this, we're gonna borrow a concept from continuous optimization, and we are going to introduce a new property for the functions for the submodular function. Okay. So sharpness has been used a lot in continuous optimization in order to improve or to prove faster convergence rates. So let's imagine for a moment that we have a concave function, okay? And we are maximizing this concave function around some nice set of feasible solutions. Okay, we have a distance d to the optimal set, to the set of optimal solutions. Okay, so this property in red, the sharpness, tries to explain the behavior of the function around the optimal set. Okay, so the behavior of the function depends how distant you are to the set. Okay. So since we are, as I mentioned, since we are assuming that f is concave, on the left we have another inequality, right? This is just a concave inequality. Okay. So I want to interpret that now, and we actually introduced this concept in submodular optimization in submodular terms. Okay. So let's say we have parameters c and theta. I'm going to say that a function is going to be a set function now. It's going to be c theta monotonic sharp if there exists some optimal solution, such as for the feasible set, each feasible set, we have this inequality now. As you can see, the distance is going to be, it's going to correspond to the cardinality of the difference to the optimal set. And the gradient in this sense is going to be the marginal values, okay? As you can see, we are summing over the elements in the optimal set compared to the set that you're evaluating, okay? So the main result that we have here is that if now we assume that the function is monotonal submodular plus it belongs to this class of function, then the greedy outputs are set with this margin, with this approximation fact, okay? So it uniquely depends on the sharpness parameters of the function. I want to emphasize that actually the greedy algorithm doesn't depend on these parameters. So it automatically adapts to the sharpness of the function. So the main the corollary in this case is that whenever theta goes to 0 and c goes to 1, meaning that it's the lower case, we recover the 1 minus 1 over 8. But if theta is 1 and c equals 1, then we recover an optimal solution. Okay, so whenever the parameters are far from 0 and 1, then we might obtain better guarantees. Okay, we also introduced the dynamic version, in which now parameters depend also on the cardinality of the set. So the behavior of the function is going to change over the size of the solution, okay, that we construct. Okay, so now the experimental results here is that we have the same type of problem, the same instances, and now we're evaluating the sharpness. We have the greedy behaving really well, and we have in dark green the curvature, and in light green we have monotonic sharpness. So as we can see, in some of the instances it's behaving better, but when we evaluate the dynamic monotonic sharpness, this refined notion of sharpness, then we obtain improved guarantees. And actually we also introduced two other concepts, submodular sharpness, so it's a larger class of functions that we can obtain better and better guarantees, actually very close to the behavior of the greedy algorithm. Okay, so you may wonder, yeah, this is some small data sets, but since our notion depends on the optimal set, we cannot do better. I mean, we cannot obtain the optimal solution for larger data sets. So this somehow explains our guarantees. Okay, so as I mentioned, we introduced other concepts such as the submodular sharpness and the dynamic variant. We proved that the submodular sharpness actually performs at least as good as the other monotonic sharpness. And we also provide some extra experiments in widely used data sets. And we show that these refined notions extremely outperform the static versions of the sharpness. Okay, some open questions here is that, are these guarantees tight? Can we do better? Can we prove better? I don't know yet. Also, can we do the same for matrix constraints? My intuition is no. It's more complicated to explain the behavior of a function around matrix. And the question is like, how can we adapt this notion of sharpness to other combinatorial settings in order to improve the approximation? Okay, that's the first part. So maybe I want to know how much time I have.
You can take another, let's say 13 minutes, 10 minutes. Okay,
good. So the second part is I want to address how flexible the greedy algorithm is. We are going to see another setting which is robust. There might happen that, for example, if we are solving sensor location, sensors are measuring different things, such as the temperature, humidity, light, etc. And we want to optimize against all of them. Okay. So we have multiple objective functions. So let's imagine the same ground sets. We have n elements, and now we have partition constraints. Okay, something more complex. The paper addresses matrix. So, but for the simplicity, just assume partition constraints. So imagine that we have different sensors in different zones, and the constraint corresponds to having a budget of sensors for each of the zones. Okay, and each of the sensors has multiple objectives. Okay, so robust meaning that we want to optimize, we want to maximize according to this constraint the minimum of these objective values. Okay, so the minimum of some modular function is not necessarily some modular. So actually that creates a problem. And Cross et al. In 2008, they proved that this problem is even hard to approximate. Okay, so there is no hope on that. So what is the challenge now is to obtain by criteria solutions. Okay, so we need to relax something of the problem in order to obtain some meaningful guarantees. Okay, so the challenge for us in this part of the talk is to provide some by criteria solutions and efficiency. And the approach, our approach, is to break feasibility. Okay, and I want to explain in a few slides what does it mean. The main theorem here is that we have an efficient polynomial time algorithm, by criteria algorithm, in which we obtain a family of feasible set. It's a small family of feasible set, but we can guarantee that we are very close to the optimal value. Okay, so you give me an epsilon, and I construct a family of feasible set. So we break feasibility, but we can guarantee that it's close to the optimal value. Okay, so there is this trade-off between feasibility violation and the quality of the solution. Okay, so what breaking feasibility means? Well, Cross et al. In 2008 for the cardinality constraint, this means just simply keep adding elements. Okay, if your budget was k, then you can keep adding elements and obtain L times k elements. Okay, but for partition constraint or matrix in general, this is not quite clear. Okay, it doesn't. You cannot apply the same algorithm. You cannot just simply keep adding elements because you may not have feasible sets. Okay, so we need to construct a family of feasible set. And for partition constraint, this means that if we had a budget kj, now in each zone we are violating the budget. Okay. So how we construct this family, and this is the role that is playing the greedy algorithm. So imagine for a moment that we have one single function, okay, one single monotone submodular function, and we are going to run greedy many times, okay. But where we run it in a function that is keeping the cumulative sets, okay. So in each iteration, we are accumulating sets in the input, okay. So once we tell this L, we have a guarantee actually that the value of the union is very close to the maximizing this single function over the feasible set. So as you obtain a larger and larger family, you are getting closer and closer to the optimal value, but you are breaking feasibility. So this is the point, how we trade off obtaining a small family, like breaking the feasibility not by much, but we are getting closer to the optimal value. So the by criteria algorithm in this sense, okay, I just reminded the problem on the top, is now we guessing opt. Opt is just a number, so we can guess it. We can construct many options for opt. And once we have a guess, we're gonna take an average over the functions, but cap the function. So why we're capping? Because we don't want the functions to have higher values. So we are controlling the value of the function. And once we have this average, we run the extended greedy on this average for this amount of times, log R over epsilon. Okay, so this just corresponds to one iteration because we have to get closer and closer to opt. So this is running in many loops. Okay, this is a binary search over opt. Okay, so what is the bad news in terms of computational performance is that finding good upper bounds for opt in this case is complicated. So it may take longer. And the extended greedy also depends on the size of the set. Okay, depends on the rank of the matrix. Okay, the good news is that we can develop as early stopping criterion. So this subroutine we're using actually give us a provable guarantee that we can obtain good upper bounds for opt. And instead of using the extended greedy, we can use a faster variant for greedy, which is called threshold greedy, that was introduced in 2014 by von der et al. Okay, that actually doesn't depend on the rank of the matrix. So let me give you some experiments. We have the same type of function, this monotone submodular, plus some perturbations. So we are creating a collection of functions. And this is just a single run, a single instance. So on the x-axis, I'm plotting the violation ratio, meaning that 1 is a feasible set, 2 is twice a feasible set, et cetera, et cetera. And on the y-axis, I have the objective values. So as you can see, this previous extended greedy on blue, you have to run up to size 6, okay, in order to realize that you're close to the optimal value, okay? But if we apply the early criterion, then the extended greedy on orange or green, the version of threshold greedy, actually needs a size 3 of the family, okay? So we can stop much earlier. And this gives a drastic improvement on the performance, okay? And the other thing is that the extended greedy actually performs less number of function calls, okay? So this is a performance profile over the different number of instances. And we can see that in almost 80% of the instances, extended threshold greedy is computing less number of functional calls. Okay, so there are more results in the paper, meaning that can we extend this to other type of algorithms like local search or something? Yes, we can do it. Is this size of family the type? So no, actually the type family is logarithm, natural logarithm. Do we need monotonicity? Yes. If we drop monotonicity, then the problem is not possible. I mean, by criteria, it's even not possible. And we can address other constraints. And also, we have an online model. And we show that, for example, for the online model, we obtain a sublinear regret with techniques from online learning and continuous optimization. Okay, so final remarks. Well, Submodular optimization appears in multiple fields. Even on my work here in the postdoc, I've been working on two-sided market design, in which actually our problem reduces to some well-known problems in Submodular optimization. But my main message is that whenever you encounter these concepts of utility and coverage, please think about Submodular optimization. It will help. It will make your life easier. That's my point. The greedy algorithm actually wins by a lot, so that's the point. It's the protagonist of this talk. And the main message first is that we can prove that provably performs better whenever we have the sharpness of the function is better. Okay. And the second message is that the extended version, it can be adapted for a robust model and efficiently. So we can trade off between this, the quality of the solution and how much you violate the feasibility. Yeah, thank you very much.
Thank you very much, Alfredo. And I think we have just a few minutes, but we have time for a few questions, maybe 1 or 2 questions. Does anybody in the audience, there's one person in the audience that maybe has a question? Nope. You can write your question in the chat, or you can, if you would like to unmute yourself, I think you have the ability to do that as well. And you can also ask Alfredo questions in the breakout rooms that will happen after David's talk in an hour about. I guess I have a very quick question, I hope, and it's probably a naive one. Mm-hmm. But so you have this multiplicative feasibility violation. What happens if you were to have an additive one?
What do you mean by additive? Do you mean
the number of, so instead of k times L, it's like k plus L or something? Are there results in that?
Not that I know. But it would be kind of the same, no? I mean, no,
yeah, I think you can.
I don't know.
You can go from. You might be able to go from one to the other and derive bounds, but I don't know if it's like the sharpest.
Yeah, if your additive is multiples of the budget, for example, yeah. I mean, yeah, but I don't know. Yeah.
Okay.
Good question. Thank you.
Okay. Well, then let's thank Alfredo again, and I will stop the recording for our first talk.